Alright, so welcome to lesson 8. We're going to revisit the chain rule in order to kind of gain a better understanding for sort of exactly what it is and in what situations we can apply it and actually have already been applying it. It's a commonly misunderstood and kind of forgotten rule that often trips people up, and so it's important that we revisit it to make sure that we have a really firm understanding of how it works. So the discovery problem has two parts. The first part is for each of the functions below, they're all called h of x. They can be expressed as the composition of two functions, f and g, as f of g of x. Find both f and g for each function below. So go through, find f and g, and then press play. We'll talk about this, and then you can move on to part 2. Okay, so hopefully the color coding gave you a little bit of a hint. I'm going to go through the first one here, and if you find that that kind of makes something click for you, then pause again and go ahead and finish the last 3. But if we notice here, there are two functions going on that I think of as the outside function, which is taking something and raising it to the 12th power. So I'll call this f of x is taking some value and raising it to the 12th power. Similarly, there is a function here, g of x, where I'm taking something, raising it to the 2nd power, taking something, multiplying it by 3, adding it to that, and then adding 4. And so what we can see is that if you take f and use an input as the function g, that you get exactly what we had with h of x. Okay? Alright, so if this made sense and now you understand exactly how to go through, go ahead and pause and go through the rest, and then I'll post the answers for those. Alright, so for all of these, we can write a function f and a function g, such that the function h is written as f of g of x. And so here we have the square root function, which is the outside function, if you will, and the input for that is x squared plus 9. So g of x would be x squared plus 9, f of g of x would be the square root of x squared plus 9. Here we have f of x being e to the x, and then h of x is when you take e to the x and you raise it to the 2x squared, and so it would be f of g of x, where g of x is 2x squared. And then here we have sine of x as the outside function, and the argument here is given by hx squared, and so we define g of x as hx squared, and now h of x is f of g of x. This is, of course, the composition of f and g, and we can also write it as f composed of g of x, and that just means that you have some function f and another function g is acting as the input for f, which is what we see here. And we talked a little bit about this. What do you do when you're trying to take the derivative of a function such as any of these functions h of x, where you have two functions composed with one another? Do you just take the derivative using the power rule, for example, here, the outside function? What do you do with the inside function? And to give you a little more intuition about this, I'm going to present you with a real-world example of how to think about the way that h of x is changing based on both of the functions that it's defined by. Alright, so here is part 2. There are 4 gears linked together, h, f, g, and x, as shown below. Each time x turns once, gear g turns halfway around. Every time gear g turns once, gear f turns 4 times around, and gear h will make exactly as many turns as f makes. So what you want to determine is what is the derivative of h in terms of x. In other words, every time x turns once, how many times will h turn? And then what you want to do is you want to think about this situation, how the different ways in which each turn are related, and then how can you relate this to the functions that we just talked about, and actually come up with a clear understanding of how you might figure out the change of the functions h in terms of f and g. Okay, so in order for us to determine how many times h is going to turn, we can't just skip to x, right? We need to know how f is going to turn, because h turns exactly as many times as f turns. But to know how many times f turns, we also have to know how many times g will turn, because g is the one that is directly connected to x. So let's just think about the situation. When x turns once, g makes a half turn. When g turns once, f will make 4 turns. And so to compute the number of turns that h will make, in other words, h prime, what we need to do is we need to think about how many times will f turn in terms of g, in other words, f prime with respect to g, and we need to multiply that by the number of times that g will turn in terms of x. And if we actually take a look at this situation, we see that this is perfectly true. G makes a half turn every time x makes 1 turn. So g prime of x would be a half. F makes 4 turns every time g makes 1 turn. And that's going to be exactly how many times h will turn. So if you multiply this out, 1/2, it makes 1/2 turn. And then f will make half of its 4 turns that it would make if g made 1 turn. So it will make 1/2 times 4, or 2 turns, and that will be exactly the number of turns that h will make. And we can clearly see how with the gears, it's important not just to have the number of turns that f makes with respect to g, but also the number of turns that g makes with respect to x, because that's how the chains are linked. And so this relates exactly to the functions that we've seen here, right? To figure out how many turns h makes, or to figure out the derivative of h, we can't just look at the function f, right? We can't just take the derivative of the function f, the outside function, because we also have to incorporate the number of the derivative of the inside function, right? Because that's actually what's driving our outside function f. And so we can use this chain rule to find the derivative of any composite function. And we're going to apply this not just to power functions as we've seen before, but we really have already applied it also to exponentials, and we can apply it to trigonometric functions as well. So here's the chain rule. We've seen this before, but it is important to copy it down again now in general, right? We talked about it in terms of power functions, and now we're talking about it just in general of any two functions that are composed with one another. If a function f is differentiable at a point u, which is equal to whatever g of x is equal to, and g is differentiable at x, then the function h of x, which is the composition f composed of g of x, which can be written like this, and I've also shown it can be written like this as well, f of g of x, is differentiable at x, and the derivative of h of x, and I've just here, each of these is just another way of writing the derivative of the composition. So I've already named h as the composition. So the derivative of h, and another way of writing the derivative of f composed with g of x, is by putting the prime notation here. So f composed of g prime of x. And if I have written it as f of g of x, then the derivative of that will be f of g of x prime. And so these are just alternate forms of writing the same thing. The derivative of this composition is given by the derivative of f with respect to g, meaning the derivative right of the outside, times the derivative of g with respect to x. So I think of this as the outside function, and I think of g of x as being the inside function. And what I do is when I see this composition, I take the derivative of the outside as if the inside were the variable, and then I take the derivative of the inside and I multiply those two together, and that will give me the derivative of the composition as a whole. Let's go ahead and take a look at a quick example before I give you a couple to try. Okay, let's say I have a function y equals sine of 4x, and I want to take the derivative of this function. What I need to notice is this is a composite function. And so it would be helpful if I can actually write what the composition is, because then I can just follow the rule very easily. So the outside function, we'll call it f, is just the function sine. And the inside function, g of x, is just the function 4x. So my function y is f of g of x, right? And so to find the derivative of y prime, I'm just using the rule here. So I want to take the derivative of f with respect to g multiplied by the derivative of g. Okay, and so now I just need to take those derivatives. So this is the outside function, right? So I take the derivative of sine with respect to 4x, meaning I just leave the 4x as if it is my input, which it is, of course, and the derivative of sine of anything is just cosine of that something. So this will be cosine of 4x, but remember, that interior part, 4x, that has a derivative as well. That's the derivative of the inside function, which is 4. And so my derivative, y prime, is equal to 4 cosine of 4x. And that is the derivative. Notice a couple of things that I did that made this a very, very simple problem was that I noticed the composite function. And so what I did was I named f of x and g of x, so that this way when I go to follow my rule, I'm looking exactly at the composition, right? It's f of g of x, and so I take the derivative of the outside function, right, the derivative of sine with respect to the inside function, and then I just take the derivative of the inside function. So always be able to identify the outside and the inside function, and that will make your life much easier. What we're going to do now is actually take a look at a lot of the rules that we previously learned, so exponential, logarithmic functions, and also take a look at trig functions, and notice how the rules for taking the derivative of these functions are really just the extension of the chain rule. Alright, so we're going to recap some of the rules we've learned, and for each of these, u is a function of x. So when I say u, I'm referring to a function that is in terms of x, and so you can actually take the derivative of u with respect to x. So the first one is simply thinking about the power rule. So if I'm taking the derivative with respect to x of some power function. And so what this is just u to any power n. Well, the way that I take the derivative of this, what I notice is that the outside function, what that is that is taking something and raising it to the nth power. The inside function is the function u. And so I take the derivative of the outside using the power rule, n times u to the n minus 1 power times the derivative of the inside, which is the derivative with respect to x of u. And this can also be written right as du dx. Right? The second one that we learned is for exponential functions. So if I'm taking the derivative with respect to x of e raised to the u power, well, what I first do is I take the derivative of the outside function. The outside function is taking e and raising it to some power. And when that's the function, the derivative of that is just e to the u again. So that's the derivative of the outside, and the derivative of the inside function, well, again here, the inside function is u, and so this is just times du dx. And of course, similarly, we have the exponential function where our base is not e, so you could have the derivative with respect to x of some positive number a raised to the u. And here again, what I'm doing is I have two functions, right? The first function is a to the x, right? And so if I call that f, then I have f of x is a to the x, and g of x is u. And so when I compose those two functions, I end up with a to the u. So I either take the derivative of the outside, and the derivative of a to the u is just going to be a to the u times the natural log of a. And then I have to take the derivative of the inside function, which in this case is u, so times du dx. Right? Again, just the chain rule being used. And if any of these are not familiar to you, go back and watch the particular video from which they came. And that way you can understand sort of why we get e to the u as the derivative of e to the u, and a to the u natural log of a when we take the derivative of the a to the u. Next, we have a logarithmic function, so the derivative with respect to x of the natural log of u. And so here the outside function is the natural log function. So I take the derivative of the natural log function, which is 1 over whatever its argument is. So in this case, 1 over u. And then I take the derivative of the inside function, which is u. So du dx. And again, I can similarly write this if it was log base some other number. So the derivative with respect to x of log base a of u. It's going to be very similar here. I'm going to have 1 over u times the natural log of a times the derivative of the inside function, which is, again, du dx. And the one that we just learned is for trig functions, right? So I'm not going to go through all of them again, but let's take a look at sine, cosine, and tangent, and then you can go ahead and add in the other ones. So if I'm taking the derivative with respect to x of the sine of u, well, here the outside function is sine, and so the derivative of sine is cosine. So I have cosine of u times the derivative of the inside function, which is u. I could also take the derivative with respect to x of cosine of u, and here I would have the outside function being cosine, and the derivative of cosine is negative sine of u times the outside function, times the inside function, which is u. Derivative of u with respect to x. All right. Derivative with respect to x of tangent of u. Just mix up, put it in parentheses for fun. And the derivative of tangent is secant squared. Secant squared u. And then the derivative of the inside function, du dx. So what you can see is that really all of the rules for specific types of functions that we've looked at are an extension of the chain rule. Because when they're a composition of two functions, I need to make sure that I am incorporating all the different pieces which contribute to the slope of the function. So if you ever need a refresher on why this is the case, go back and take a look at the chain analogy, and that way you can really comprehend why it's so important to take the derivative of the inside function and the derivative of the outside function in order to find your derivative. I'm going to give you a couple to practice and be ready to present tomorrow. All right, go ahead and complete these 4 problems. Make sure that you identify the outside and inside functions if you need to use the chain rule, and then follow the rules that we've already discussed for taking the derivative of trigonometric functions, exponential functions, power functions, so on and so forth. Make sure that you just take your time here and identify each rule that you need to use so that you don't lose a small but important piece of your answer.